Hi, I'm going to introduce select and nest in this video, and we're going to be looking at the roots of a function. It's going to be sine of 2x squared. This one it's not too difficult to find the roots sort of more or less analytically, but just this will illustrate how you can find virtually any set of roots within an interval, no matter how complicated that function is, as long as it's differentiable. So define the function and plot it here. And we can see that there are quite a few roots. Now find root, we'll find one single root, and what you do is you provide the function. You could optionally make this f of x equals 0, but just if you give it an expression, you'll find the values where it's 0. And second argument is the variable and the initial guess, or first point now. So this by default uses Newton's method, which we'll look at a little more closely in a few minutes. And it locates the point with x equal to 2, takes a tangent line and drops it to the x-axis. That's the next guess, and it continues until you get close enough to a root. Again, we'll look at that more closely. If you can imagine that the algorithm is going to converge to this first root if we evaluate this expression, which 1.65 is right around here. So the way to find several roots at once is to use this find root function as a function with the initial point as the variable. So starting at different initial guesses, we're going to get different roots. If we were to have started at 2.5, chances I would have gotten the second root. So we're going to map this pure function. Okay, so the pure function takes as its input a number, and that number is the initial guess, and we get a similar result, a single rule for a root of the function. We're going to map it over a range of numbers from 0 to 2 pi in steps of 1/10 of a pi. So we're going to get about, 21 results. Okay. So it looks like that. First time I did this, I was getting some messages, and I guess I didn't. I had already shut off the message. If you get a message and it's okay, so notice that there's some duplication here, and there's also convergence to numbers that are outside of our interval between 0 and 2 pi, like the first 3 guesses. So what we're going to do is we're going to do two things. We'll first extract just these numbers from our list of rules. And so we take x and map this. We're going to produce the same list of rules right here, the same input as above. But when we replace x with each of these numbers, we're going to get a list of those numbers, like this. Okay. So essentially what's happening is for every one of the lists of rules, we get a number. So call that rule list. And now we're going to use something that we haven't seen before, and that's the select function. So select takes a list and only keeps the elements of the list that satisfy the second argument, which is a Boolean condition. And this condition is quite simple. It's whether or not the number lies in the interval between 0 and 2 pi. Okay, so this pure function is true if the input is between 0 and 2 pi, false otherwise. So by selecting, notice we lose the first three numbers and maybe a few others, I'm not sure. But all these numbers lie in the interval. Okay, so one other thing the final thing I'm going to do is to do with this list to see if it's complete. And the easiest way to see if it's complete is to plot these points on the x-axis in our graph. So we take the same plot and use something called epilogue, which takes a list of graphics for primitives. And I won't, we'll be coming back to graphics a little later, so I won't dwell too much on this, but essentially what this does is after the plot is created, I do a few things. I set the point size to be a certain size, which I fiddled with to make it look effective. We'll talk more about that later. And then we map the function called point, which sets an ordered pair to be a graphical point. Map the point, the number, which is the root, followed by 0, which gives us a point on the x-axis. And we map that over this this list from root lists that lie in our interval. So I'm copying this select expression down from what we have above. So here's what we get. Okay, so all these points are points that were identified in our root list. And you'll notice that it's not complete. And the reason it's not complete is our mesh of initial values wasn't large enough. So what I'm going to do is I'm going to make a quick edit and go through this whole process one more time. Okay, so the map expression here was copied down. I'll only change this one. And instead of every 1/10 pi, I'm going to multiply by 10 and have it every 1/100th pi. So I've got a lot more initial values. The list is going to be 10 times longer, and many of them are going to get filtered out in our next step. So we're going to be selecting only the numbers that lie between 0 and 2 pi. And once again, this expression gets copied down here, and so doesn't have to change that. If I do the plot again, notice that it's hard to maybe tell exactly, but it looks like every one of these roots was identified. There's a point where at every point where the graph goes through the x-axis, it looks like. Okay, so this list we have up here, I guess actually we don't see it here, so I'll evaluate this. This list is the list of roots. And actually, no, there's one other thing I meant to do. There's duplication here, obviously, you can see. So what you can do is apply union to this. Take the union, which removes the duplications, and I probably want to do that here because I think I'm actually plotting a lot of these points over several times. Anyway, here's our complete list. Now, moving on to something else, as I mentioned, find root uses Newton's method by default. There are other methods that you can select, and derivation of Newton's method is fairly simple, but it boils down to if you have a guess at a root, you compute this quantity, which is the guess minus the function evaluated that guess divided by the derivative. That's Newton's method, and so we evaluate this function step, which takes a guess and produces the next guess. This will usually converge to a solution. Now you have to be careful. There's one condition, one situation where you run into problems, and that's where the derivative is 0. So it turns out that with our function that we've been working with at 0, get a strange result, which I think, I'm not sure exactly what that will end up being. If I change this though to, say, 2.0, our next guess is 1.58, which is closer to the 1.65, which is the solution. So let's actually go through this. We still have the same function, sine of 2x squared. I'm going to have to redefine that. F of 2 is sine of 4. If we compute step 2.0, which we just did, it's 1.582. Let's look at the value of the function at that point. It's 0.14. Now if we take that number, take step of 2.0, and apply step to that, we get 1.65, and f of that, you can see, is quite small. And if we continue, we'll get closer and closer to the to the root. So this process of taking a number and applying a function multiple times can be automated simply by using a function called nest. And let me illustrate that with an undefined function f and an undefined input a. If we take nest f, a, and 5, what this does is it applies the function f to a 5 times. So this is the result. Okay, and this number here can vary anywhere from 0, for example, which gives us, applies f no times, up to any number of times, like 15, for example. So we can apply this function using step and 2.0, and let's do it 8 times. If we do that, we get a number that we've seen already, 1.6514, and this output, I'm going to use the notation percentage sign as the previous output. If I apply f to that previous output, you can see you get virtually 0. Okay, so that's nest, and nest there's 3 other related functions. There's nest list. The difference between nest and nest list is nest list goes through and gives you not only the final result but all the previous results. So if we take that, and the example we just did starts at 2, and you can see that by the time you've reached 4 steps, so 3 steps I guess, after that there's no real change, although that's only the display value. There are some changes that with less precise values that you don't see. There's another nest, and that's actually would be useful if we wanted to program Newton's method more efficiently, and that's to nest while. So you take the same function like step and initial guess, but you keep nesting until while this condition is true, which is that the absolute value of the function is greater than some tolerance. So here it's within 10 to the negative 6. So there's the convergence set to the same number, and there's also a nest while list, which also gives you the list of intermediate results, including the last one. So that's nest. We'll see that as a useful function in addition to select, which we saw earlier. The select function takes a list as its first argument and a Boolean function giving you a true or false as its second, and produces the sublist of values that make the Boolean function true. And nest takes a function and as a first argument, a starting value for its second, and a number of steps for its third. That's it. I'm going to skip the limit direction to for a different video because I'm running out of time.